So now that you've had a chance to explore a little bit with tangent lines and circles in GeoGebra, it's time to go through two important theorems related to circles and tangent lines, specifically related to a single circle and lines that are tangent to that circle. So first, as a brief review of that terminology that we saw before, a tangent line is one that intersects a circle once and only once with an intersection point called the point of tangency. Here, point T is the point of tangency because the line containing T intersects the circle with center A at exactly one point. If we have multiple circles and lines that are tangent to both, we call those lines common tangents, and we name the common tangents according to whether or not they cross the segment that connects the centers of those circles. So if the line, like the beige one, doesn't cross the segment connecting the centers, we call it an external tangent. If it does, like the yellow tangent line here, we call it an internal tangent. We also saw that circles themselves can be tangent to each other because they are tangent to the same line at the same point of tangency, and we call them externally tangent circles if neither circle contains the center of the other circle, or we call them internally tangent circles, like the diagram at the right, if one of the circles, in this case circle A, contains the center of the other circle, that is, circle with center C. So now that we've seen that, there are two important theorems to go through as it relates to tangents. The first is called the perpendicular tangent theorem. And the perpendicular tangent theorem says that a line that is tangent to a circle is perpendicular to the radius of the circle that ends at the point of tangency. In this case, we have the blue circle and the black line being tangent, and we have the radius that intersects the circle at the point of tangency. The perpendicular tangent theorem says that that angle is a right angle. So go ahead, pause the video, copy down what you see on the screen, come back when you're ready to see an explanation of why this is true, and then move on to the second theorem. So this is not actually a difficult theorem to prove because it follows immediately from something that we've seen before. If we extend this radius down to its diameter, then we have, in fact, an inscribed angle that is made by a chord of the circle, because remember, the diameter is a chord, along with a tangent line. And we've seen in previous videos, and you worked with before, the fact that when that happens, the measure of the angle is half the measure of the arc that's intercepted and contained within that angle. Well, this particular case, the arc that is contained is a semicircle because it is made by a diameter. And we know semicircles have a measure of 180 degrees. Therefore, the inscribed angle made by the diameter and the tangent line that is intersecting the circle there is 90 degrees because 90 is 1/2 of 180. So there we go, perpendicular tangents to the radius at the point of tangency. The second property or theorem that we're going to see has to do with what happens if two lines or two segments are tangent to the same circle and they intersect outside the circle. In this case, this is the congruent tangents theorem, and it says the two segments that originate from the same point that are tangent to the same circle are congruent. So go ahead, pause the video, copy this down, and see if you can create a proof based on what we know before for the fact that these two tangents are going to be congruent. One thing you might consider that will help a lot is to draw a segment that connects the center to the intersection point of the tangents and see what you can do there. So go ahead, pause the video, copy it down, and see if you can come up with a proof on your own. Come back when you are ready to see the proof and then wrap up the video. So let's go ahead and see that proof. Here we added some auxiliary lines. We added some names to the points. AD and BD are the two tangent segments. They intersect at D. The circle is centered at C. We have that common side CD, which is the segment that connects the center of the circle with the intersection point of the two tangents, as well as radii AC and BC. So we know we are given that AD and BD are tangents, and we want to prove that AD and BD, the segments, are congruent. Well, because they are tangents, and because AC and BC are radii, we know that they are perpendicular by the perpendicular tangents theorem that we just saw. So what that would say is that angle CAD and angle CBD are right, or are 90 degrees, because of the perpendicular tangents theorem. Okay, great. Well, because they are both 90-degree angles, they are congruent to each other, and it's important that we have this in two steps because it really is two separate things. One is that they are perpendicular because of the perpendicular tangents theorem, and the other is that they are congruent because all right angles are congruent. Let's make that an S there. Okay. Cool. Well, that's helpful. Now we have two right triangles, and right triangles are easier to show that they're congruent than other types of triangles. Now that we have that angle, all we need to know are that the hypotenuse and one other set of sides are congruent, and we can use hypotenuse leg. Well, the hypotenuses of these two triangles are congruent because they're both CD, and CD is congruent to CD by the reflexive property. And we know that I'm going to start doing this proof up above the circle here for a step and then move down there. So I'll just draw an arrow. And we know that AC is congruent to BC because they're both radii of the same circle, and all radii of the same circle are congruent. Great. So DC congruent to DC, AC congruent to BC. And there we have it. We have two right triangles where the hypotenuse and one leg are congruent, so those two triangles are congruent. In this particular case, triangle ACD is congruent to triangle BCD by hypotenuse leg. And then by corresponding parts of congruent triangles being congruent, the most helpful of those pieces of congruent triangle proofs, CPCTC, AD is congruent to BD. So if you need to pause the video again before it ends to copy down any stage of the proof, please do that. But those are the two major theorems related to tangent lines and single circles. One is that a tangent line is perpendicular to the radius that intersects it at the point of tangency, and the other is that two tangents that are tangent to the same circle but that intersect outside the circle, the segments between the point of tangency and the intersection points of those tangents must be congruent.